Good afternoon, everyone. Welcome to the HPL seminar this week. Today, I would like to introduce our speaker, Dr. Delyle Polet. Delyle did his undergraduate at the University of Alberta and achieved 2 bachelor's degrees in physics and bioscience in 2013. Then he came to the University of Calgary for his master's in mechanical engineering under the supervision of Dr. Dave Ribel. In 2015, he started his PhD at the same university here in biological science, working with Drs. John Bertram and Jessica Theodore. During his PhD, he worked on quadrupedal locomotion, reduced gravity running, and energy optimization in legged locomotion. And I believe that part of these works has been already presented in the HPL seminar previously. He achieved his PhD degree early this year, and now he's been working as a research assistant with Dr. John Bertram's Integrative Biomechanics Lab. When I asked about his current research interests, he said he's interested in almost anything within comparative biomechanics. He is currently working on legged locomotion right now, but he also has been interested in the mechanics of flights, non-wetting biological surfaces, and fish swimming. Aside from his academic background, he also introduces himself as a husband and a father of 3 kids under 5 years. And he also says that he enjoys playing jazz piano, reading books, and catching bugs. But I'm not quite sure if he really meant that catching real bugs or debugging his MATLAB code. So anyway, today he will be giving a talk entitled as Running Post Reviewed Through Reduced Gravity. Whenever you're ready.
All right, thank you for that introduction. So yeah, this is my 3rd talk at the HPL, and the first 2 were on quadrupedal locomotion. So I figured I might as well show you that I do actually care about human beings as well. And I have studied them with reduced gravity. And so this work I did with my supervisor, John Bertram, and Ryan Schroeder. Okay. Oh dear, there we go. So there's kind of 2 parts to this presentation. The first part, some of you may have seen in my previous presentations, and it was mostly published in the Journal of Experimental Biology in 2018. The second part is a bit of new stuff that we've learned about this data set since then. But really the motivation for this work is to try to understand why normal is normal. And what I mean by that is that we can look at a typical healthy person running and point to subtle differences in terms of gait, but overall the gait remains fairly consistent among different people. And it's interesting that these patterns are so consistent when there is so much coordination going on and so many different possibilities in terms of what the body can do. And I think that the difficulty of coordination and different possibilities are well exemplified by the video game Co-op, where players are tasked with actuating the thighs and the calf muscles separately, and they find it really difficult to move around and come up with quite interesting ways of getting from one place to another place. So given so many alternatives for moving around, the big question is, why is normal gait normal at all? And one of the hypotheses that we try to explore is that normal is normal because it's less costly. What you see here is a metabolic cost surface where each of these different patterns of movement have a different metabolic cost associated with them, which is a function of various gait parameters. And the idea is that normal gaits lie at a minimum on this surface. And so one way to test that human beings are sensitive to these cost surfaces and that it's a priority of the motor control system to be economical is to change the circumstance so that there's a new optimum and see if people seem to adjust their gait accordingly. So one such novel circumstance is being on another planet. And we didn't have the budget to send anyone to another celestial body. But we can imagine what it might be like. So before I play this clip from a Hollywood person's sort of idea of what running on Mars looks like, I just want you to imagine what you think running on the moon or running on Mars would be. Would you bounce more? Would you bounce less? Would you use a completely different gait? And so just think about that and have that in your mind before you see the results of our study. So in this movie, John Carter, this fellow from Earth, finds himself magically teleported to Mars, and he's experiencing Martian gravity for the first time. And this is how he responds. He takes these huge leaps through the air. And of course he can, because he has muscles that have developed in normal gravity. He can jump really high in the air. And I think that most people, when they think about moving on a different planet, they think that they would run with these huge leaps through the air. And that's perhaps also motivated by observations of the few people that have actually been to a different celestial body, the Apollo astronauts. And they did seem to have quite unusual gaits in gravity. But it is also hard to tell if this is from the reduced lunar gravity or if it's from their bulky spacesuits or both. So what we can do, we can fake reduced gravity here on Earth with this fancy apparatus designed by Andy Ruina from Cornell. And basically all these contraptions interact together to provide a constant upward force through a harness that counteracts a person's weight. And so their effective weight is lower. And you can read more about the design of this in this preprint on bioRxiv. But through it, we can simulate gravity as low as the moon's, which is 1/6 of Earth's gravity. Okay, so I'm just going to sort of give you the answer. So I asked you before what you think the difference would be between running on Earth and running in the moon. So here's one of the subjects that exemplifies this. What we're doing is tracking this marker in the back, and in normal gravity, there's large oscillations. We can see the takeoff and the maximum height and measure the distance between those two. And that's about 6 centimeters, this very bouncy gait. Once we get to lunar gravity, the run becomes completely flat or mostly flat. We can measure the distance between takeoff and the maximum height. And we see that there's a huge reduction in the height. And because there's a reduction in the excursion, the height excursion during the flight phase, we also know that the takeoff speed must be a lot lower because this is lower gravity. So any particular small takeoff speed should result in a huge increase in height. But obviously people are not choosing that, even though they could. So our question is, why isn't running on the moon bouncier? People should be able to jump with huge leaps, but they don't. And I think our intuition leads us astray here, because we often think of the flight phase as being completely free. That if you're flying through the air, you're not really actuating any muscles. So this should be a low-cost portion of the gait. But in fact, it actually costs us a lot of energy to jump really high, because we need to insert a lot of energy into our body and able to achieve these high velocities. And every time we touch the ground, so there's our takeoff velocity, every time we touch the ground, we lose a bit of that energy as well. And the best analogy for this is thinking about skipping a stone. When you want to skip a stone, you don't just throw the stone straight down at the water and it bounces back. You have to go at a very shallow angle, because that vertical velocity needs to be small so it doesn't break the surface tension. And so that's the same idea when we're running, is if we have a smaller vertical takeoff velocity, we lose less energy per step to the ground. And so we can think about reducing our energetic costs by taking more steps, and then we'll have a very small takeoff velocity. And if we double the number of steps, we actually have about half the number of energy we need to achieve these different steps. But of course, the problem here is that even though we use a very small amount of energy to get ourselves off the ground, now suddenly we're taking really, really frequent steps. And that could be energetically costly as well. So there seems to be a trade-off between what we call cost of collisions and cost of frequent steps. And what we did is develop a model to sort of approximate this trade-off for our system. In this model, we think of the human as just a point mass. And right before they touch the ground, they have a vertical velocity v and horizontal velocity u. They touch the ground with a vertical leg and instantaneously lose all that vertical velocity. And then they have to reinsert it with muscular work at a cost of mv squared over 2. And then voila, they've now had what we call a pseudo-elastic collision where they have the same energy out of it that they started with. But we're approximating the stance phase as just an instant of time with a vertical leg, which of course is an approximation. That's not how people actually do it, but we'll see if this leads to good predictions. So that's one part of the cost. And the second part has to do with the frequency of steps. So we'll call that frequency f. And we'll say that this cost goes to some exponent k and is multiplied by some proportionality constant. Now, if we're thinking about work of swinging the legs, which is perhaps the most intuitive aspect of frequency-based cost, then it costs us quite a lot more to swing the leg more frequently. And in fact, that cost increases with frequency squared. Now, what we're interested in finding is a cost surface that combines the effect of vertical takeoff velocity, which is a parameter we can measure in people and that they can choose, and gravity, which is a parameter we can manipulate. And so we can use simple ballistics, since we don't have any time in the stance phase, to figure out that it takes us the time v over g to get to the apex of the flight, and we just invert that to get the frequency. And so now we have a cost surface, which is a function of our vertical takeoff velocity and gravity. And it looks like what we have is two portions. We have a cost that increases with vertical takeoff velocity squared, and a cost that's inversely proportional to vertical takeoff velocity. So I think this is easier to understand if we actually visualize this cost surface. So what we have here is energetic cost as a function of vertical takeoff velocity. This is for Earth gravity. We see that the collisional cost increases with velocity squared. The frequency cost is inversely proportional to velocity, and they add together to make this bowl shape with this optimum vertical takeoff velocity up here. So let's see what happens when we cut the gravity by half. Well, what happens is that the frequency cost decreases, but the collisional cost as a function of takeoff velocity doesn't change. And this might be surprising at first glance, but it kind of makes sense if you think about, say, 2 meters per second squared, 2 meters per second being the same amount of momentum, whether you're on the moon or whether you're on Earth. And so it costs the same amount of energy to get up to that speed, and you're going to lose all that energy once you hit the ground again. So it doesn't matter whether you're on Earth or you're on the moon. But if you're on the moon, that 2 meters per second can get you a heck of a lot farther and keep you in the air for much longer, giving you plenty of time to swing your legs very cheaply. And so what happens is the collisional cost, it has the same response as vertical takeoff velocity, but because the frequency cost goes down, we actually shift to a new optimum where the collisional cost is lower. And this trend continues as we lower gravity, and we get a whole suite of predictions now. Yeah, so it's quite interesting to think about that. In fact, this cost that we associate with stance might be a lot lower not because of the stance cost itself, but because this frequency cost or this swing cost has reduced. And that is something that was found and published in 2019 by Simpson and colleagues. This video seems to be sort of cutting a bit. Let me see if I can refresh it. There we go. That's a bit better on my end. Hopefully it's better on your end as well. So what they did is they created an exoskeleton, what they call an exotendon, which is essentially a rubber band between the legs. And that just helps the subject to swing their legs more quickly. And you can kind of see, it's a little subtle, but you can see that the person on the left has a higher frequency gait than the person on the right. And that higher frequency ends up reducing the cost of the stance phase considerably, because the person doesn't need to expend as much energy to bounce high in order to swing the legs more quickly. This is what we predict as well in our case, and we have a whole suite of predictions based on our model. And now we can say that what we anticipate is that the vertical takeoff velocity should scale with gravitational acceleration to the 1/2 power, or the square root. And so we invited 10 subjects at 5 levels of gravity each to run in our harness at, in this case, a horizontal speed of 2 meters per second. And these are the results, and it fits the predictions beautifully. And this effect is not subtle either. At normal gravity, we have a vertical takeoff velocity of about 0.7 meters per second, whereas in lunar gravity, it's about 0.3 meters per second. So that's a 1/2 reduction in takeoff speed. So what we learned from this is that low gravity running is less bouncy than high gravity running, which seems counterintuitive. But it comes from 2 simple principles. 1, that there is limb work associated with ground contact, and 2, that there's a cost for frequent steps. In this case, we're thinking about swing work. And it's really that cost, the cost of swing work, that leads to a bouncier gait in normal gravity. That the only reason we run with a bouncy gait in normal gravity is because swinging the legs is expensive. And again, this work is published in the Journal of Experimental Biology. And I don't know how you want to do this. Should we pause now for questions or go to part 2 before we continue?
You give an entire talk first, and then we'll have question and answer period afterwards.
Okay, perfect. All right. So far, this has been a nice, clean, and tidy story. But you'll notice there's an asterisk here. So we've just talked about swing work, and we've just talked about one speed. But in fact, it's not so simple. And we did look at other speeds as well. We went up to 14 kilometers an hour, which is about 4 meters per second. And we went as slow as 0.5 meters per second. So each participant had 5 speeds, 5 levels of gravity, 25 trials each. And what we found is that for each particular speed, the trend seemed to work as a function of gravity. So once again, we have vertical takeoff velocity as a function of gravitational acceleration. And we have 0.5 meters per second, 2 meters per second, and 4 meters per second. And in each case, that square root of gravitational acceleration prediction fits really, really well. Although it fits better at intermediate speeds. And we also see, though, that there is definitely an effect of speed, that at lower speeds, there seems to be a higher takeoff velocity than at higher speeds, higher horizontal speeds. And this is not what our model predicted. As you can see, our total energetic cost is independent of horizontal speed. And that's because we modeled the stance phases being on completely vertical legs, which of course is not true. When people run, they have excursion of the limb, a finite contact angle, and the stance phase, it takes appreciable amount of time. So there should be a fore-aft deceleration and acceleration that we're not accounting for. What we can do is we can look at the vertical takeoff velocity. We can shift this a little bit and look at the vertical takeoff velocity as a function of horizontal speed now on the x-axis. And here we have the highest level of gravity up here in green and the lowest level of gravity down here in blue. And for each case, again, you see a reduction in the vertical takeoff speed as horizontal speed increases. But something weird is going on at normal gravity, where it seems like these 2 data points are outliers, where the vertical takeoff velocity is really low and there's this high variation. And so what we did is you can kind of partition the subjects into 2 groups. 3 of them seem to have really high vertical takeoff speed at slow speeds, and the rest of them had really low vertical takeoff speeds at low speeds. So what's going on here? Well, what is actually happening is that one group has a flight phase and their feet completely clear the ground, and the other group has a grounded run. We only instructed our subjects to run. We didn't say how. And so what we're looking at is two different interpretations of what a run is. For some subjects, a run means your feet actually have to clear the ground with every step. And for the other group, all it means is that you can kind of take a bouncy walk. And so this is obviously a psychological effect, something that they're trying to follow the instructions of the experimenter, but the instructions aren't clear, so they're making their own interpretation. So that's one aspect of it, and it clearly has very little to do with energetics. But there's also an aspect of the energetics that are more complicated than I said in part one. So you'll remember the second part, this frequency-based part, originally I just left it as an exponent k. And this exponent can mean different things depending on its value. So let's think about three different values, 1, 2, and 3. For an exponent of 1, we can think of this as an impulsive cost, a cost of impulse. And by the way, these three costs are coming from Art Quo's 2001 paper, where he talks about these different costs in a very simple walking model. So an impulse cost, the way to think about this is if you're swinging your leg back and forth really quickly, your leg has to have a higher velocity than if it's swinging slowly, even if you're running at the same horizontal speed, because it's going back and forth more times. That means it has to have a higher momentum, and producing an impulse with your muscles costs a certain amount of energy. We know that even if your muscles aren't doing any work, if they're on and producing force, there's a cost associated with that. An exponent 2 is a cost of work. And so this is that force multiplied by the distance over which it acts. And that's one that we've used so far. And then the higher exponent, exponent 3, is what Art calls a force time cost in his paper. Later on, he and others have called it a force rate penalty. I like to think of it as an activation penalty or an approximation of an activation penalty. Basically, the idea is that turning your muscles on and off really frequently leads to higher costs as well. And so we can determine which of these swing costs best fits our model by using a log-log plot. So we have log of the takeoff velocity against log of gravitational acceleration. And the slope of this line is going to tell us something about that exponent. So when the horizontal speed is really low, we can see that this red line, which is the best fit of the data, the least squares fit of the data, is really close to that impulse line, which is right here. And there's two other lines, a line for K of 2, which is work, and a line for K of 3, which is activation, that are actually outside the 95% confidence interval for the slope. Now, as we increase speed, that slope moves up a little bit. And then at 2 meters per second, the slope is much more closely aligned with a work-based cost. And as we keep going, eventually it's very closely aligned with an activation or force rate cost. And we can plot this, there are best fit K, or K as a function of treadmill speed. Here's the best fit in the red, with the red markers. We can see that the best fit K increases as speed increases. So what this kind of looks like is that different costs have different dominance at different horizontal speeds. And this sort of makes sense if you think about what these different costs might be physiologically, as well as their responsiveness to frequency. So this is just a plot I made up earlier today, but the central idea is that if you have one response that is to frequency to the first power, it's going to dominate at lower speeds, and that there should be a sufficiently low speed at which it will dominate as long as all of these pass through 0. And then if you have a frequency squared cost, depending on its scaling relative to a frequency third cost, there could be a region where it dominates as well at intermediate frequencies. And then the frequency third cost eventually will catch up to the frequency squared cost and dominate the high frequencies. And so we can think of that at higher speeds. Eventually, there's the amount of force you have to produce, as well as the number of frequent steps you have to take, will cause this activation cost, or this force rate penalty, to be quite expensive. But so far, these are very heuristic ideas. We've used an extremely simple model, and that was partially by design. We wanted to understand every aspect of the model we were working with. But we would like to use more physical models, such as the one over here, which has been used to understand reduced gravity in the past. And that can give us a little more information about fore-aft deceleration, as well as how all these costs might not only affect swinging the leg, but also the cost during stance. For example, if you're taking really frequent steps, even if you're not swinging your legs very much during those frequent steps, you still are turning your muscles on and off with every step. So there will be an activation penalty there. For now, though, I think there are a few take-home messages we can take from this analysis. We seem to be able to account for the effect of gravity on takeoff speed as long as we control for horizontal velocity. And that it's this trade-off between the cost of collisions during stance versus the cost of frequent steps. And running is essentially bouncy because frequent steps are expensive. We need to give ourselves enough time to to swing our legs forward, to let our muscles cool down, and so on. We can't yet account for the effect of changing speed. We're working on it. Some of this seems to be psychological, for example, grounded running at really slow speeds and high gravity. And the dominant frequency-based cost seems to change as we change speed, which sort of makes sense. Later, we also want to know what portion of this cost is due to swinging the legs versus the stance phase. Yeah, so that's all I have for now. Thank you for your attention, and I'm happy to take questions.
Thank you, Delyle, for the great talk. If anyone has any questions to our speaker, please use raise hand button at the bottom of your screen, and I'll just call on you when it's your turn. I'll then now open the seminar to the questions. Does anybody has any questions to our speaker? Actually, let me ask a good question, Delyle. So I'm actually not familiar with this field a lot, but in the first study, I saw that a great apparatus where it holds the entire body so that we can kind of experimentally simulate the decreased gravity while we run or walk. But I kind of feel like it is still a bit different from the real environment of decreased gravity, because I think I could still go much higher as well, as farther each step as I go or run. So I guess my question is, how does results from using that apparatus could be really related to the real environment of decreased gravity?
Right, so the question is whether the apparatus we've created is actually representative of actual reduced gravity. Now that's a great question. And the shorter answer is it's a decent approximation, but it's not perfect. So here's that apparatus again. Basically, the whole idea is it's just pulling up on the body, but that's only going to reduce the force on the center of mass. It's not going to change the effect of gravity on each of the limbs, for example.
Okay.
So this is potentially an issue, especially when we're talking about leg swing costs, right? So one of the things that we know is that the natural frequency of a pendulum should go, let me see if I can get this right, should go down as gravity decreases, for example, right? And that swinging the legs, the work of swinging the legs is minimal at your natural pendular frequency. So there should be, so that's going to affect things a little bit. Um, that's the main thing though, because this apparatus is pretty good. There is a little bit of fluctuation in terms of the force produced by the harness versus your position in this plane, but it's not very big. And so we do think that it is providing a very constant upward force against the center of mass. But it's just against the center of mass. It's not against these other ones. And there's other things that people have done. One, of course, is to take people on a plane and do a parabolic arc.
I see.
Which has been done, but you're limited to very short trials. Another is to put people in a machine that's on the side. Mm-hmm. So it restricts your motion to being very sagittal, but at least if you've set it up right, you should have the same reduction in gravity for the limbs as well as the body. We find that this particular setup has a lot more freedom, as well as allowing for more extensive trials as well. So.
Thank you. I mean, since we are on the same slide, is the blue line covering or wrapping the body is like a cover, kind of rubber band, or is it just?
So this here.
Yes.
What you're talking about? Yeah, those are just straps. Let me see if I can show this in action later on. Yeah. So you can kind of see the whole thing here. They're just straps, and then these are plastic bars. Try to keep this all very low weight so that this isn't adding any extra inertia. Yeah, that's it. And then it's a. I think that John actually designed the harness himself because there just wasn't a design that was appropriate for this particular system.
Thank you. I see Hansel, you have a question. Please go ahead.
Okay, do you hear me?
Yes.
Yep. Delyle, I thought it was nice that you added some conditions with different speeds, and your explanation on how different cost exponents on the frequency would make the difference made sense to me. But that also raised some questions. So I thought your motivation is to see whether humans choose their movement to minimize energy. And you use some simple model to see it. And when you see some conditions that doesn't quite go with it, one approach is to modify your model, where another approach is to say, okay, human doesn't minimize energy.
Right.
So maybe that's a bit hard thing to distinguish, but do you have any idea on how to distinguish them, or how to avoid the problem of making models just even more and more complex?
Right. Yeah, no, that's an excellent question, and I think one that we all, as you know, I don't know if I should use the term model-based experimenters, fall into all the time, because we always want to make a great model that explains everything. But you're right. There's a risk of overfitting our data in a way, and I think that there's a few aspects to this. One is that the fit is really good if you ignore the effective speed. So I feel like that is telling in some ways, that even though this model is super simple, there's really hardly any ingredients, it still fits really, really well as a function of gravity. Now that could be a coincidence, but it would be really nice, and it would be ideal if we could actually measure people's metabolic cost as they change, as they move on this system. And we can do that. It just extends the length of the trial. And if you're doing 25 different trials, and of course in that case you would want to get them to jump, say, with a very high, with a really bouncy gait versus not. It's just going to be experimentally very difficult and take a really long time and be hard on the participants. I think another approach is maybe to think of a better alternative hypothesis. And one that I've been thinking about that is not really energetics based is simple like spring mass model stuff. So if an alternative hypothesis is, say, for example, well, maybe it's not that people are changing their gait because of energetics, they're changing it because they want to maintain a constant leg pseudo stiffness. So if they're trying to be like a mass on a spring, maybe they just want to keep the same stiffness at every level of gravity. And I feel like that could be something that we might be able to test. The problem with that model is you do need to have velocity as an input into your model, or you have to constrain certain parameters because it's not fully determined at any particular speed and stiffness. So I'd have to think about how we would do that. But I think maybe that's one of the solutions is actually comparing the energetic hypothesis with a model, whether it's a simple model or a more complex one, and compare that to another hypothesis that is not based on energetics, but is based on something else, and seeing which one is more predictive. Does that make sense? Do you have any suggestions, Hansel, of what I could do?
No, I will need to think hard.
Okay.
But maybe we will talk again. Thanks.
Yeah.
Okay, I think I saw Benno, you raise your hands or...
Also, if I could interrupt, I might be seeing people that are trying to raise their hands, and I know that I had trouble with this last week, but I think if you click on the participants button, that's where you can find the capability of raising your hand. Anyway. Yeah. Just in case people don't know.
So yeah, I mean, I thought, but I still saw Benno. Do you have any questions for Delyle?
Yes.
Okay, let's go ahead.
A few years ago, we had a running symposium here in Calgary, and we had two speakers talking about this topic about movement on lower gravity.
Yep.
One speaker was Minetti, who made a model, a mathematical model. And the other speaker was Kavanagh, who had some picture from actual movement on the moon from astronauts. And both had the same result. The result was that the movement was not a symmetrical movement, but was more like a galloping movement.
Yeah.
Now you don't have anything like that here.
No.
Can you comment on that?
Sure. Yeah. No, that's really interesting. So can I ask first of all when this symposium was?
That's when I retired. That's about 6 years ago.
Oh wow.
And as a matter of fact,
2014.
Yeah, that's 6 years.
Oh man,
yes.
I wish I'd gone to the symposium.
And as a matter of fact, I just saw recently a model from Vandenbogert, who has as one possibility to change the gravity.
Yeah.
And he gets the same result. The result is a kind of a little a galloping movement when you go to lower gravities.
Yeah. Right. So that is quite interesting and something I've thought about. So Minetti's study. Okay, let's actually take a step back. So there was this observation that the Apollo astronauts often would use a skipping like gait, or I think the term, what do they use it? Can't quite remember, but it's not quite the skip that we use on Earth, where we sort of switch the leading leg. They use the same leading leg every time, I think. Anyway, so it's quite unusual because normally we don't do that. Minetti's study actually measured the metabolic cost of people running and skipping and maybe walking as well. But what they found was that skipping approaches the metabolic cost of running at low gravity. So they were about the same cost, but skipping is never cheaper than running. And so that's interesting. And I think the suggestion in that paper was that maybe it's something about the suits that the astronauts were using that pushes skipping over the edge and makes it more cheap. And then Van den Bogaert's model, they did find that skipping should be cheaper than running. And now the cost function I find really difficult to understand. They had some measure of muscular effort. And at the time that I read this paper carefully, which was a few years ago, I didn't really understand how they were measuring metabolic or muscle effort and what the physiological basis was of that. So I guess all I can say is that my feeling at the time was a bit skeptical of that cost function, but it's also been a long time since I read it, so I would like to go back to it. In terms of the mechanics of why would skipping be cheaper in lower gravity than higher gravity, I don't know, but I think that's a really interesting question and one that I would like to explore.
Okay, I see Tim, you have a question. Please go ahead. Tim, yeah.
Now?
Yes.
Yeah, now you can hear me. Okay.
Yeah.
Sorry. Yeah, thanks for the interesting talk, Delyle. I have a question about the plot of the log V against the log G. Maybe you can show that.
Yeah. Oh dear. Hold on a minute. Okay, here we go.
Yeah, so here you sort of see that the work is in between the impulse and the activation. And so in your other plot where that you just made today, like the speculation plot with the frequencies, you sort of say that it could be that at lower horizontal speeds, it's an impulse cost, and then at higher, it's an activation, and in between it's the work. As an alternative, could it just be that the work cost is not important, or, well, yeah, the other two costs are important, and the only reason why it has a good fit for intermediate speeds, it's that is where both costs contribute equally. Could it be an alternative interpretation of this? Or?
Yeah, I don't see why not, to be honest with you. Yeah, I hadn't really thought of that. That's true.
Well, it's very interesting because I think in your original paper, I haven't read it yet, but the Journal of Experimental Biology, you're just saying that the work cost is the best one. Yeah. Right? And so I am, of course, interested in the force rate cost, and I was surprised that wasn't the best one. But so it could be that it's something like this then. Yeah, definitely. That's a really good point, and really difficult, I think, to parse out, right? Like I think you would. I don't know how you would do that experimentally, and then in a model, I guess in a mechanical model, you could start to figure that out if you had a few more components that you could play around with. But no, that's a good point. Yeah, I don't see why. Yeah, if you just had the two costs, I could see that if you had them both at, say, equal costs, that it would look something like work. Yeah. Okay. Cool.
Okay, thank you. I think Kun, you have a question. Yes, please go ahead.
Yes. Okay, so actually this question is related to someone's question. So of course I was also thinking about the fact that you do not really reduce gravity in the sense that you do not change the natural frequency of the lag by imposing this force. So the question's already been asked, but by now I think I've perhaps found a suggestion for a solution, which is inspired by the other thing you showed of the spring between the legs, right? So you could conceivably, because gravity just acts as a spring in some sense for a swinging pendulum, right? Gravitational force is just a spring. Yeah. And so you could conceivably manipulate the
the natural frequency.
Yeah, exactly. You could manipulate this natural frequency in a way that is consistent with your gravity manipulation by adding springs of different stiffnesses between the legs. Yeah.
I love it. I love it. Let's do it.
It's cool, huh? Yeah.
No, that's a great idea. I mean, I don't know how you do it with the arms.
Yeah,
but,
I was thinking about that also, but that I think the arms you will just have to ignore.
Yeah, for sure. No, that I love that idea. I guess that's one way you could potentially at least just show that, determine whether it has an influence, I guess, on the gait chosen.
Yeah.
So,
but I guess in your model, actually, in your model, you could have accounted for it, right?
That's right. Yeah.
So
well, that's not entirely true. So if you're talking about the super simple impulsive legs with a frequency squared cost, then no, not really. I mean, I guess I could say frequency minus natural frequency squared or something like that.
Yeah, I was just chatting about that with Ryan, actually. It's like, yeah.
But I don't know that it would make that much of a difference, honestly. One of the things we did do in the paper is one of the reviewers had a question about this, that, you know, the legs are swinging at the natural frequency. You know, we can't really control for it, but what we did was we saw whether, it's been a few years, so I can't quite remember, but somehow we incorporated the leg length into it as well. And we showed that if you use the leg length as another predictor, it doesn't really change the results at all. So you would think that, like, people with, say, shorter legs would have a different response than people with longer legs, but that's not really the case. There's a little bit better fit if you include leg length as well, but not much.
Okay.
So, yeah.
Cool.
Anyway, still a cool idea. I would love to do that experiment. Yeah.
Okay. Tim, do you have more questions, or did you just unloaded hands?
Yeah, I forgot to lower. I didn't know you had to actually lower it.
It's fine. Well, actually, let me ask you more question, Delyle.
Mm-hmm.
So you've mentioning like a better cost or more expensive, but I have no feeling yet about the cost. So would the better cost mean like using less energy so that we could make a better performance in using our body, or could you just explain about this more for me?
I don't know that I understood the question. You're talking about cost?
Like, yeah, so the cost difference, but I'm not actually sure about the more expensive costs, or like a different cost would also affect like a performance.
A different coast?
Yes, I mean you compare like a costs or energy consumption, right?
Yes.
Yes.
Yeah. So,
and
yeah, we looked at different costs.
Yes.
Let me just go back here, I guess. This is kind of the two costs we're thinking about. The first one being associated with what we call a collisional cost, so touching the ground, losing a lot of that momentum and having to resupply it. And then this one is due to frequent steps. Yeah, but then your question though is about performance.
Yes.
So, like, are you thinking, what exactly are you thinking? Like using?
I don't know. I just have a feeling that there might be some relationship between the two, or.
But between these costs and performance and running, or
running, let's say.
Yeah, so there is, and I think that's better studied, honestly, in this paper by Simpson and colleagues. Let me just go back to the reference, so you can look that up. And I think it really does a good job of explaining how say you have less cost in stance because of a reduction of cost in swing.
Okay.
It does a really good job, and they suggest various applications for their exotendon, as they call it, in terms of, I don't know, helping people who may just be starting running and want to get a bit of a performance boost or whatever. But I mean, I think that the main takeaway though is that it's a way of probing how all these costs relate to each other. To me, that's the most valuable thing, rather than as a performance enhancer. Like even the reduction of cost that they see here due to the exo tendon is small. It's measurable, but it's small. And then in terms of the reduced gravity apparatus itself, I don't think it's really going to help anyone train with running. Like I do know that they use it a little bit in physiotherapy, but not this apparatus, like a different one that's sort of a cushioned treadmill. But apart from that, I don't think it would really help with athletic performance, because it's not really providing any sort of challenge to the individual.
Thank you.
Yeah.
Yep, Walter, please go ahead.
Thanks, yeah. And my apologies. I was in a thesis exam, and so I only dialed in at about 1/4 the hour there, and so I didn't see the beginning, and so some of the stuff might have been explained. But just coming back to the particular video that you showed right now, there with the elastic band between the limbs, when I just qualitatively look at that, to me, the most significant thing seems to be, and again, I'm not sure, that might not be verified if you do a quantitative analysis, but just qualitatively, the person who takes the shorter steps on the left there with the rubber band in between, she also seems to have a much smaller excursion of the center of mass in the vertical direction. And I would assume that would probably make also a difference. And I'm not familiar with this. I just wonder if that was analyzed in this particular context.
No, that's almost certainly true, and that is why I bring this up, is that the excursion of the center of mass on the left is smaller, which is exactly the same effect that we found in our study, and it seems to be related, right? Like there's a reduction in swing cost here because of the elastic band, which means that you don't have to bounce as high in order to swing your legs efficiently. And that's the same thing in reduced gravity. There's a reduction in swing cost because a very small velocity will provide you with enough time to swing your legs forward. So I think that's exactly the same. In this particular study, the Simpson study, I'm not sure if that's one of the parameters they quantified. You can check the paper though and see. But yeah, qualitatively, it seems pretty obvious.
Do you know if they compared the runner as well? When she had the rubber band between the legs and then took the shorter strides, with the runner taking those short strides without the rubber band between the legs? So how much of an effect is the shorter strides and the smaller excursion compared to the free running at a certain speed with the rubber band between the legs? Would they get a similar reduction potentially in cost if the person just took the shorter steps and the lesser excursion?
I think I don't think so. I can't remember if they quantified it that way. You have to look at the study.
Yeah, sure.
But I'm pretty sure that you wouldn't. Certainly, if the principle that they're putting forward holds, that if you had the same step length and same excursion, you would be basically having to swing your legs really fast, and that would cost you more. I could pull up the study right now and just quickly.
No, don't. Please don't.
Okay.
The other very simple question that I had is, why would you measure speeds as slow as 0.5 meters per second in running? That's really not a running speed. And on the other side, why not explore higher speeds? I saw you went up to about 4 meters there under the normal gravity situations, and a good runner can very easily run for long periods of times, you know, at 5.5, 6 meters per second. And I also find that when people run faster, they run very differently. You know, I always say there's a sprint running, that's one style, and then there's a jogging, which you essentially analyze, which is another style, and then you have runners, you know, that run 10Ks comfortably, you know, there's some people that can very, very comfortably run a 10K in 30 minutes. And, but their running is completely different. It's a completely different style. And so I was wondering if across, you know, if your thing would be applicable across an entire range of speed rather than in the, what I would call medium to very low unrealistic running speed.
Right. So the key is some people can run this fast. I think most people find it very difficult to run more than 4 meters per second for a long period of time. So these trials were only 2 minutes long, but at normal gravity, some participants could not sustain could not sustain 4 meters per second for 2 minutes.
I realized that, but you know, you could easily select people who could do that if you want to explore that.
We could have selected that. We decided not to, partially just to make recruitment easier, and also partially because we feel like these effects are not. We don't want to make it seem like these effects are just something that athletic people would be sensitive to. We believe that all people to some degree are sensitive to metabolic cost, and that it's a basic aspect of the human motor control system. So, but then you're right. I mean, it does provide some limitations, because if our upper bound is 4 meters per second, we also wanted a significant, like a large enough spread in the velocity. And so that's why we chose the low speeds, because that gives us, you know, an 8-fold contrast in horizontal speed. But then you're right, it introduces these weird problems because that is super, super, super slow, that no one ever runs that slowly unless they're told to. And then there's this effect of like, well, what does that even mean? I think though that we can still parse out some of these effects, and it remains to be seen, but I think that even though it is unrealistic under normal circumstances, we will be able to see the response of velocity with, the response of vertical velocity with horizontal velocity by including these low speeds.
Another thing that I was thinking about when I saw your, you know, your weight reducing, gravity reducing apparatus, you know, one thing, of course, is that you kind of try to simulate gravity. And I was thinking what you're actually doing from a muscular point of view. And, you know, we all have a certain amount of strength in our muscles. And of course, when you then take part of the weight off, then we become lighter. And presumably the ratio of the strength in our muscles that we have relative to what we need per step running at a certain speed becomes easier then. And then I was thinking, would therefore your model potentially also apply to heavy and light people? You know, like would a very heavy but fit person adopt a running style that looks more like a more gravity type of a running style, and a very light runner would adopt more a running style that looks more like a smaller gravity running gait, or is that pushing the thing too far? Have you ever looked at anything like that? Or in other words, you could put additional weight on people. Would they adopt a higher, what would resemble more a higher gravity gait, for example?
Yeah, so it is a different thing. We are reducing people's weight, but we're not reducing their inertia.
Yeah, no, right? I realize that, yeah.
Right, so I believe the comparative analysis you're looking for has been done. I think Roger Cram published something on this a few years ago where he looked at the effect of adding weight to a person versus simulating, I think it might have been hypergravity in that case. I'd have to look up the study and check it for you. But I honestly haven't looked into it very much. In terms of the effect that we're thinking about, like that you need higher velocities to account for leg swinging, in that case, it wouldn't matter so much what your whole body mass is, but more what your leg mass is and what your leg distribution is. And there have definitely been studies done where people have added weights to people's legs, and they were interested in measuring metabolic costs, but I don't know if they looked at how the gait changes. And my suspicion is that if you have heavier weights on the leg, you're going to take on a bouncier run. That's my prediction based on our results. So you can test that at home and see if I'm right or not.
Thank you.
Yeah, no problem.
Okay. I see, Michael, you have a question?
Yes. Whoops. Thanks, Delyle.
No problem.
Interesting as always.
Thanks.
My question was with the low speed running again, mostly if this really like high knee gait that some people adopted seems pretty costly for such a low speed. Since you gave them 2 minutes to kind of habituate to the condition, did they change over the 2 minutes?
Ooh, that's an interesting question. And I don't know. Well, there might be a, oh, sorry about that. There might be a signal in the data. Let's see.
I mean, my thought is that people would converge to a similar gait if given enough time, but.
Yeah, so that's interesting. So what we do see is more variability in the people that had the weird gait at low speeds. Mm-hmm. And it's hard to tell if that's a function of just that, like, there's a signal to noise ratio where, if you provide more takeoff speed, you're more likely to have more variability. But that also doesn't seem to be the case here where, say, for example, the takeoff speed's still higher, but the noise is the same. So I wonder if maybe some of that variation is from people sort of slowly reducing their takeoff speed as the trial goes on. It'd be interesting to see. I'm 100% sure that this gait is the economical one compared to this one. So yeah, no, that'd be something we could look at in our data for sure.
Cool, thank you.
Yeah, no problem.
Okay, Siska, please go ahead.
I was just wondering if you know of any studies that looked at running with the suits, like the astronaut suits in the simulated environment, and if they could replicate this.
Yeah, I think that has been done. So looking at people wearing astronaut suits in reduced gravity. I seem to remember coming across that paper. I mean, at the time, it really didn't tell me anything that I needed. Like, they weren't measuring the things that I'm interested in, like takeoff speed and that sort of thing. But I think they did look at that. And I can't remember if the astronauts ever did take on a skipping gait in that circumstance or not. I could find that paper for you and send it to you if you want.
Thank you. Yeah, I was just wondering if you would be able to replicate this lope, and if it would be because of the suit or, yeah.
Yeah, I mean, you should be able to, right? Like, if it is a combination of gravity, reduction of gravity, and weird suit, then yeah, reduce the gravity, put a weird suit, see if it happens again. That's the natural test to do for sure. And yeah, I think it's been done. Part of the issue in that case is, again, even if you do use an apparatus like what we have, you're not really simulating the full thing, right? Like you're not reducing the gravity on the limbs as well, and that might be part of the issue. So, yeah.
Thank you.
Yeah, good question. Thanks.
Ansel, please go ahead.
Yep, I have a question on the maybe adaptation or initial learning. So I imagine if you given low gravity all of a sudden and people keep producing, say, muscle force as much as they did in normal condition, they may jump off and then find it's not so nice and maybe adjust their gait, or they may find it, I don't know. So do you see any initial learning when you do the experiment? Does it take time? And how does it feel? Do they feel like, oh, I don't like flying off? Or do they feel like, oh, it's more tiring to do it, I may need to change it? Yeah. So any comment on that?
Yeah, great question. Most, obviously people's self-reported assessment of the run was not something we were really measuring, but we did ask people and people wanted to talk about it. I think a common sentiment, I guess, was that at low gravity, you feel really unstable. And having tried this out myself, I can attest to that. At low gravity, it just feels like you barely touch the ground and then you go flying. So it feels really weird because you feel like you don't really have as much control over your body. And I wonder if that's true, right? Like, I wonder if you actually have more control. And I wonder if I can actually look at the data. Yeah, for example, like you see at low gravity, the variation in takeoff velocity is quite low, right? So it doesn't really seem like people are actually not controlling their vertical takeoff velocity. That seems to be very well controlled. It could be that the step position might vary from step to step. But it does take a while to get used to that effect of feeling like, oh, okay, gravity has changed now. Like, you feel uncomfortable at first, but after a while, it feels great, honestly. Like, you can just go forever. And, the people that had trouble at 4 meters per second in normal gravity had no trouble at low gravity. They could just keep going. Did that answer all your questions? I feel like there was another question you were asking.
Oh, maybe another question would be, I don't know, maybe halfway you answered, but okay. I was wondering, whether people directly feel the objective function of energy to change their behavior.
Oh, yes. So you asked how quickly people adapt. They adapt very fast.
Very fast.
Yeah, very fast, I would say. I guess this is something we could quantify and could and should quantify how quickly, the variation in takeoff velocity changes or other parameters. But just having looked at the data, it seems like it's right away. Like, there really is not much there. I mean, there really isn't much time anyway. Like, it's just 2 minutes at each trial. So yeah.
So you're saying people changed their behavior quite quickly, and that's consistent with your energy optimization model, but maybe people didn't really comment on, like, they felt it's tiring, so they changed it, but rather...
Yeah, no one commented on saying like, oh, I tried jumping really high and it felt costly, so no one ever said anything like that. And it almost makes it seem like it's not energy optimization in that it happens so quickly. Like, that almost makes it more suspicious to me, because you look at all these other studies like Max Donnellan and Sanchez and other people that have looked at things like adaptation to split belt walking and adaptation to exoskeletons. And, they find optimization or, adaptation towards reducing energetic costs in a lot of cases, but usually it takes a while. Like, usually it takes a lot of experience with the exoskeleton or experience with the treadmill. I think with the treadmill study, they found that people weren't actually arriving at the optimum until 45 minutes in. And so to me, it seems like there's one of two things going on. Either it's such an obvious change, like the signal for increasing your velocity, your vertical takeoff velocity is so large, like there's such a big cost that it's a very obvious change, or something else is going on. like our body is measuring something else that makes us feel more comfortable at that gait. And maybe that's a good proxy of energetic cost that we use. And maybe that's what we're responding to. But it kind of makes me think that because it's so fast, I don't know that we're actually really responding to energetic costs, or we're responding to something different. Mm-hmm. It happens to be energetically beneficial, but I'm not sure we're responding to it.
Yeah, interesting. Yeah, thanks.
No problem.
Okay, I see Rob. You have a question? Please go ahead.
Yes, it's perhaps more comment than question. Comparing the astronauts who were running, if you call it that, on the moon, and saying, you know, would they do the same sort of skipping behavior on Earth in your frame? They actually had an additional constraint when they were on the moon, and they were formally told to be very stable because they didn't want them falling over and tearing their suits while they were up there.
Oh,
and so they were actually formally warned to protect against that. So they would be, while they're jogging along or skipping along,
yeah,
they would have been very conscious of stability. And I could imagine when I saw John's harness, one of the first things that occurred to me is you'd feel like a little child. You had, you know, you could play, you'd feel stability was not anything you'd have to worry about.
Mm-hmm.
And because I've always been very conscious on treadmills that it's a very different gait to being not on a treadmill. And so you could actually be on a treadmill and feel, well, I don't care now, the harness is going to protect me. So something that disappears when you put more and more protection with the harness is this consciousness of stability and maybe any economic cost of having a stable gait. Any thoughts on that, Delyle?
Yeah, sure. I mean, that's an interesting point. It's not one I thought of or was aware of, but I guess that is true. I mean, tearing your suit on the moon is bad, pretty bad. There's like a pretty big penalty there. Yeah, and I mean, there's a certain, I guess, idea of maybe that does explain the skipping gait on the moon, that you know, our participants did say, like, you know, they feel unstable just touching the ground with like one little pinky toe and going flying. So maybe if you use 2 feet, you feel a bit more stable. Yeah, I guess the way of testing that experimentally would be to put people on a parabolic, on a plane with a parabolic trajectory and tell them that the suit is expensive, and if they fall over, they have to pay for it. I don't know. I feel like you could start with the easy experiment, right? Easy as in finding an Apollo astronaut suit and putting it on someone and putting them on a reduced gravity treadmill, and just see if, you know, is that enough to elicit the transition to skipping? And if it's not, then you could ask yourself, well, is there this additional constraint? But you know, no, it's a good point. I hadn't thought of that.
Okay, Tim, please go ahead.
Can I just add?
Sure.
We don't understand the dynamics of skipping. There are scaling effects that haven't been sorted out yet. So little children spontaneously skip when adults do not spontaneously skip. So the interaction between gravity and the skipping gait is not well understood. And Delyle didn't do that study. He asked the subjects to run. And so that's what they did.
I'll just add, thank you, John, for that comment. I'll just add too that I am interested in skipping, and you know, we've played around with a lot of really simple models, and one of the models that I played around with does spontaneously skip at sufficiently high, at sufficiently low speeds and high step lengths. So in that particular model, skipping gait kind of emerges just if you have if you're constrained to use a large step length at a sort of intermediate speed. So take that for what it's worth. But that's an experiment I want to see. Like if we make people take a constrained step length during running and we get them to skip versus run, is it cheaper to actually skip? So if anyone wants to do that experiment, let me know.
Okay, Tim, please go ahead.
So running, I assume with reduced gravity is cheaper in terms of metabolic cost, but running is not possible at zero gravity.
That's
So
right.
If you ask people to set their gravity, what do you think they would choose?
What would they choose?
So if they have a button that links to your apparatus,
yeah,
they can just press the button to increase and to decrease. What do you think?
Oh, that's a good question. I mean, it's hard to do with this apparatus because I'll be honest, at low gravities, it starts to hurt because now suddenly the harness is holding most of your weight, right? And that's going through thin straps that are going right through your crotch. It hurts. Okay. And so I think people would probably choose, because of that, like a higher level of gravity. If you could make it super comfortable, I'm not sure what they would do. I mean, astronauts talk about zero G as being like the best thing in the world once you get used to it. Like you just, everything feels effortless, at least moving around does. So I think probably if we could choose, most people would probably choose zero G because then you get to fly. Like, how cool is that?
But how do you come back to the ground then?
Well, why do you need to come back to the ground? You're flying.
Yeah, okay, fair. I have a second question. Just curious. So for your slowest speed, you had these two groups. One group sort of walking and the other group doing the weird running thingy.
Mm-hmm. Yep.
Do you regret not being more specific with your instruction? Or are you still happy with that decision to keep it like more free, what they can choose?
I have mixed feelings about it, to be honest with you. I think it's kind of interesting that people have such vastly different interpretations of what running is. I think I think my philosophy as an experimenter is to try to give as few instructions as possible, because we want this to be a natural adaptation, and we don't want to manipulate the results, even if it's subconsciously, right? So I think in general, I'd err on the side of just basically be like, here are the two rules that we're giving you, and that's it, right? So, you know, rule 1, stay on the treadmill. Rule 2, run for 2 minutes. Like I think that's I prefer, from like just a philosophical I guess argument, just keep the instructions as minimal as possible.
Okay, that's right. Thanks.
Okay, Walter, do you have any last question?
Yeah, a couple more comments in the talking about running, and when you said I don't know how to define running, I always defined running by you're a runner or you run if you're concerned with time. You're a jogger if you're concerned with losing weight or fitness or that type of thing. So I never really thought of running and as a matter of more as a matter of attitude rather than speed.
Right.
And the other comment I wanted to make is I thought it was interesting when we talked about skipping, because I always felt skipping shows a mental attitude, because when kids, or I actually know some adults who skip, but skipping seems to be reserved when you're in a certain frame of mind. Typically, I would associate it with a good mood. I've not seen kids skip when they're angry. They run or they walk away, but they don't skip. So I always thought it was actually very interesting that we have this particular gait that I at least feel, without having studied it, to be associated with some kind of a mental state. Yeah. But a couple of questions. When you reduced gravity, did you see that people change their footfall patterns? Most people are heel foot strikers when you took up some of their weight. Did you observe that potentially they became more forefoot strikers?
I don't know.
I didn't pay attention.
I didn't pay attention to that, to be honest with you.
I was just curious about it, and I thought that probably would be happening.
Yeah, I would guess so. Yeah, like I would suspect that as you reduce gravity, you probably see more toe running.
That's my experience.
Yeah. Okay. So there we go. I mean, we can actually quantify it. I mean, we still have all the video, so that is something we could look at for sure.
It's just because, a while ago there was always this big debate about rear foot strikers and forefoot strikers, and that was, I've always been kind of curious why some people feel really comfortable midfoot, forefoot striking, and some people just can't do it, and the other way around. Like, I feel really, really awful when somebody tells me to have to run with the heel first, touch with the heel first. And I always had the feeling it has something to do with strength relative to body weight, and so I was wondering about that. And then, of course, again, when you reduce weight with your apparatus, then I would assume that people are more tend to run on the forefoot. And the other comment that I wanted to make is, the graph that you have on the left there, the vertical takeoff velocity as a function of speed. I think it's fabulous. Where as speed increases, and I assume you take away options of how people do that, the variability becomes smaller. And I'm curious if you think if you went to higher and higher speeds, if that variability would go down to zero and everybody would converge at the same vertical takeoff speed.
Yeah, that's a good question, and I kind of suspect that probably they would. I think that there's just less you can. You have less, basically less freedom, I think, in terms of
less freedom. I think, you have less possibility, and I think it might go to a similar or same value.
Right, and I think like even in terms of like an optimization framework, I think the costs become so large that the solution becomes very obvious. So like any deviation away from that solution is met with an instant and very high penalty. And I think that once you get up to a high enough speed, all the costs become so large, like the cost of swinging your legs, you can feel it. The cost of touching the ground, you can feel it. That those signals become large enough that there's that you kind of know once you're in that optimum is my feeling.
Thanks.
So just to add real quick, since I was a participant in this study as well as a co-author for this study, Delyle might not remember, but I definitely remember that at lower speeds, you're definitely not landing on your heel. It's all toe running at that point. And then I also kind of remember what John was saying, that at low gravities, I think that was also true, but especially at the low speeds.
And yeah, that's something, again, going back to the running meeting that Benno was referring to earlier, because I had, at that meeting, I was talking about heel-toe running, and I had everybody stand up, and I said, everybody's a toe runner naturally, and then I had everybody stand up and say, okay, now jog in place. And of course, if you jog in place, that means you have zero forward velocity.
Right.
Nobody hits the ground with the heel first. Everybody hits the ground with the forefoot first. So at zero speed, that's definitely true. And I would assume at very slow speeds, that becomes true as well.
Yeah, exactly. Yeah.
Okay, on that note, I think we should slowly wrap up. I would like to thank Delyle again for sharing his great work. For next week's seminar, we'll be hearing from Scott Seibel, and the title is Toward Understanding a Day in the Life of a Chondrocyte. Thank you all for coming today, and I'll see you all next week.